Okay, in our last video, we saw how to come up with the formula for various ionic compounds. Today, what I want to do is talk about naming those compounds. All right, and naming simple binary compounds is pretty straightforward. What you want to do is use the following system where the name is going to be equal to the metal. Like I said in the video, the cation is always listed first, following your nonmetal stem, let me put a space in there, so nonmetal stem, and then you want to follow it up with an IDE suffix. All right, so what does the nonmetal stem mean? Well, I've got a good table for you in your book, but it's fairly intuitive once you see it. So let's go ahead and take a look at this table from your book, including the non-metal stems. So for example, if your non-metal is bromine, then that stem is just going to be brom. If it's chlorine, it's going to be chlor. If it's fluorine, it's going to be fluor. If it's iodine, it's going to be iode. If it's nitrogen, it's going to be nitr. If it's oxygen, it's just going to be ox. If it's phosphorus, it's going to be phosp. And sulfur would just be sulf. So it's pretty easy to remember these because they tend to flow off your tongue the best when you're naming them. But let's take an example of this. All right, so let's do NaCl. That was one of the binary compounds we looked at in the last video. So in this case, its name would start out with the metal. So in this case, sodium is our metal. So we just say sodium would be the metal. And I'll just underline this as red. That way we know that it's metal. We've color-coded it to up above. Then we have a space. And then after that, we need to include our nonmetal, which in this case is going to be chlor. So I just write chlor. And then the suffix would be IDE. So the name of NaCl would be sodium chloride. And like I said, the IDE is attached directly after the nonmetal stem, but you do need a space between the two. All right, so it's not really that bad naming these. Sodium chloride is actually just table salt. It's something you have in almost everybody's kitchen. So if you want to impress everybody, you can say, "Can you pass me the sodium chloride?" when you're at the dinner table. All right, let's try another one. All right, let's do calcium with 3 of them and nitrogen with 2 of them. So it's Ca3N2. And let's come up with the name for this. So Ca, like I said, is just calcium. So that's our metal. Our cations always go first. And then we're going to have a space. And then we want to include the nitrogen nonmetal stem, which in this case is just going to be NITR. And then we want the IDE suffix. All right, so as you can see, we're kind of following the same scheme that we did up above, and it's usually pretty intuitive, right? So if you forget the non-metal stem for nitrogen, you can just try a bunch of variations. So would it be calcium nitride? That doesn't sound very good, but nitride flows off your tongue a lot better. Honestly, I think that's how they went about kind of coming up with these prefixes and suffixes. All right, let's try a different one. And this next one's kind of interesting. And I wanted to make a note that transition metals can have various charges. And this really complicates things for naming. So let's take an example here. So let's say we've got copper and it's copper 2+. Copper can exist as copper 2+, or it can exist as copper 1+. Whoops, so let's compare both of these. So I'll just do copper 1+ down below. And let's go ahead and compare each of these. So what happens when we combine each with chlorine? Okay, so we could have copper 2 plus combined with chlorine, which chlorine's always going to be 1 minus, or we could have it combined with copper 1 plus down below. All right, in each of these situations, we're going to get a different ratio, right? So in this top example, if copper is 2 plus, that means we're going to need 2 chlorines to cancel out the positive 2 on the copper, right? So this would be CuCl2. Where down below, it's already balanced. So we could just write CuCl. Whoops, sorry, this should be a U up here, not an L. So if we were to name these, we couldn't just call them both copper chloride, right? Because then we don't know which one we're referring to. Copper chloride doesn't tell you whether or not you're talking about the top example or the bottom example. Okay, so let's make a note that copper chloride doesn't tell you which you have, right? Because it just tells you you've got copper and chlorine, but we don't know in what ratio. Okay, so with transition metals, what you need to do is use a Roman numeral. And the workaround, use a Roman numeral after your metal to indicate charge for your cation. Okay, so let's go ahead and take a look at each of these. And in fact, I'm going to move my note kind of off to the side here, and let's try to name each of these. Okay, so in the top example, it's quite clear that we had copper with the 2 plus. So if we wanted to name this, what I would do is I'd write copper, and then in Roman numerals, 2 chloride. And then for the bottom example, where copper had a 1 plus, I would just say copper 1 chloride. But this avoids the ambiguity of just calling something copper chloride. If we just say copper chloride, we don't know if we're talking about copper 1 chloride or copper 2 chloride. So we need that Roman numeral to help us differentiate. There's also another system where you use ik and us. That's really old school, and I don't expect you to know that. It only really works in situations where there are only 2 possible states for a cation, meaning it could either be positive 2 or positive 1 or positive 2, positive 3, but I really hate using it. The Roman numeral system is a lot better in my opinion. So that's what we're going to be using in this course. All right, so let's go back and take a look at the idea of the smallest unit of ionic compounds. And let's go ahead and view sodium chloride. And sodium chloride is just NaCl. All right, so sodium chloride is in this big 3-dimensional network over here. And let's go ahead and paste this picture in here. So this is sodium chloride. And if we look at this, this is called a crystal lattice. And really all a crystal lattice is it's a 3D network of anions and cations. And they kind of stack in this big brick, right? So the purple spheres, like I said before, are sodium. The big green spheres are chloride anions. and electrostatically they're attracted to one another because they have opposite charges. All right, so in this case, you can see that a sodium ion is in this corner. And what that means is that it's a lattice site. So a lattice site is an occupied position within that crystal lattice network. So it's kind of interesting to think about. And like I said, sodium chloride we represented as NaCl because that is the simplest ratio of cations to anions. So even though it could be sodium a billion and chloride a billion, it's still a 1-to-1 ratio, so we just simplify it and say NaCl. All right, so let's think about the formula weight. So the formula weight is going to be the sum of the atomic weights. Shown in the formula for ionic compounds. So let's take a look at an example here, and we'll do sodium chloride. So NaCl. Okay, well, let's grab our periodic table. And if we grab our periodic table, we can quickly look up, oops, sorry, I forgot my L there. We can quickly look up the atomic weight for just sodium right here. So in my periodic table, sodium is 22.99 U. Okay? And then chlorine in my periodic table, if I look it up, is going to be 35.45 U. Okay? So if we go ahead and we add all of these together, I'll just quickly do that. We're going to get our formula weight, which in this case is going to be equal to 58.44 U. That doesn't mean that the entire crystal lattice weighs this amount. It just means that the simplest ratio of cations to anions weighs this amount. This is different than molecular weight. If you notice, we're saying that this is specific for ionic compounds. Molecular weight is the same, but for covalent compounds, which we'll talk more about later. All right, so that is a differentiation. We'll go back and practice this later, but if we had, let's say, CO2, which is covalent, we'd find the mass of one carbon and then find the mass of two oxygens, add them together, and we'd have our molecular weight. All right, let's do one more example here before we finish up. And let's do Fe2O3. And in fact, let's try to come up with the name of this too. So if we think about kind of reversing this to the cations and anions, we could say, well, let's just do that flipperoo trick that you showed me before. And if we break this apart, that means that the iron must have a 3 positive charge, right? Because we'd have to pull the 3 up into that position. And that means that the oxygen, conversely, would have to have a 2 negative charge. So if we were to name this, this would be iron. And then because it's got the symbol 3, this would be iron, 3 oxide, also known as rust. So make sure you can go from the name to the cations and anions to the formula itself. It's really helpful to practice this over and over again. All right, so what is the formula weight? of iron 3 oxide. Okay, so let's try to figure this out. Well, if I go to my periodic table, I could look up the mass of iron. So, or actually, I'll just say atomic weight of iron is going to be 55.85 mass units, right? Where oxygen, on the other hand, has an atomic weight that is a lot less. It's going to be 16.00, right? So let's try to figure out the overall formula weight. Okay, so we've got one iron atom times 55.85, or shoot, we have two iron atoms, excuse me. So this is two atoms. So we need to multiply the mass, or sorry, the atomic weight of the iron by 2 to account for each of those iron atoms. Okay, so we've got the iron taken care of, and now we need to do the oxygen. So we've got 3 oxygen atoms. And we need to multiply that by the atomic weight, which is 16.00. And now we can type this into our calculator, and this comes out to 159.70 units. All right, and it is important to remember that back when we talked about the mole, we said that 1 mole of a given substance, in this case iron 3 oxide, is going to be equal to its formula weight in grams. So in this case, it'd just be 159.70 grams. So this is a really useful conversion when you're doing a lot of these math problems. Another one that's pretty helpful too, just before we continue on, is we know that 1 mole of iron oxide is going to be equal to 6.022 times 10 to the 23rd units. So we could say that there's that many units within 1 mole. Both of these are useful conversions. I just figured it'd be good to review these before we continue on. All right, I hope that helps. I know a lot of this is tricky. The name of the game here is practice is key. I would try to do as many practice problems as possible, both from your book and from the practice worksheets listed on Canvas. All right, I hope that helps.